Any questions? Yes, Elizabeth Ann.
So I know we have videos online. Would you prefer us, or would it be easier for us to watch the videos before class, or would it be better to watch it after?
It depends on your learning style. Personally, I would think if you watch them beforehand, then you can come in with questions automatically. And so I think that probably would work best in general. So, any other questions? Yes, Rena.
As we go, we should turn the master set to Blackboard. Should we also include their homework questions from textbook?
The homework questions from the textbook are for your practice and understanding. Since I give the solutions, you're not going to turn in the ones from the textbook.
And these ones, like how clear should it be done? Should I explain why I pick up certain option before I give it to you?
Ask that again.
Should I explain why I picked up A or B or C when should I write here why I choose this, or it's just enough to?
I'm not quite sure I'm following the question. So,
like when we give a master set for grading to Blackboard,
right.
Should we explain why we pick error options?
If I don't say explain, then it's not required.
Okay, so I just like this and it's
Yes. There's some where I do explicitly say explain, in which case I am looking for that. If you, on multiple choice, if you just give the answer without any explanation, then it's basically all or nothing. If you give an explanation, you can potentially get partial credit.
And when we should give number, should we give step by step or how we calculate it?
That would be nice. Again, the more steps you skip, the less partial credit. Yep. Other questions? Yes. Right. In my nice ideal world, which is not going to happen, but in my ideal world, everyone's going to do the same thing. Everyone's going to do it online, or everyone's going to do it on paper. That's my preference. And more realistically, just one or the other. Occasionally, somebody would do both, but I'm not necessarily going to grade them at the same time, just because if I'm in a paper pen mood, then I'm going to do the ones that are handed in on paper. If I'm in an electronic mood, I'll do those. So I think that was a vague enough answer, but whichever one. If you are submitting it online, please make sure that you read the syllabus about how to submit it online in terms of file name or format and format. Or Newton's first law. Well, the master set is, for chapter 2, is old test questions.
Okay.
So that should give you some idea. Also, I have old tests posted if you wanted to look through those. Under supplemental material, then I think old tests, something clever like that. Other questions? All right. Now, we're not going to do a lab today, for better or for worse. One thing that I'm going to go over, and I know I have several videos on this already, but it's important enough that I do want to go over it And we're going to end this section at least with a test level problem, but you need to get there first. So we talked last time about forces. What we'll get into today, the big thing is our force diagrams. How many of you have watched the videos of force diagrams already? All right. Hopefully you will not be too bored. All right, so there's basically a checklist. And each of these represents a force. So some of you have seen this. Anybody want to just show off some of the stuff you learned?
Friction, tension, other weight, normal.
Yes. There we go. So we'll talk about sort of each one independently. So there is symbol. So we'll start out with that.
Lowercase f.
Yeah, I call it sort of the Baroque F. I put a little extra swirl in there, but just some people will do a capital F with a lowercase f. But, all right, so we got friction. F sub T. And the reason I don't use a capital T for it, some people will on the first test use capital T for tension. I know what you mean. The reason I don't is that near the end of the course, we will need capital T for period. And there's, I feel like it limits some of the confusion later on by starting out with F sub T now, as opposed to later on changing it.
Problem dependent. Lowercase w.
Uppercase W is reserved for the unit of watts, or more specifically for us, is uppercase W we'll use for work.
Capital Y.
Now for weight, weight is a specific case of force due to gravity. If we're dealing with a general case of force due to gravity, F with a lowercase g here. So both of these sort of fall into this category of gravitational force. There are forces, therefore there's a direction involved. So we have the direction with respect to objects and direction with respect to each other. It's one of those things that forces come in pairs, and so that's when I talk about direction with respect to each other. If I have a force, if I have a friction force acting on one object, I know there's got to be a friction force acting on another object. Oh, and requirements. And there's also what's required, what has to be there in order for these to exist. First off, normal. What is the normal force?
Contact.
Okay, so that's a requirement right there, contact. Why is it called normal? It's a math term. That's pretty much the answer that I get from most of my classes. Somebody might know. Normal in math means perpendicular. So what one of the things about normal force is that it is perpendicular to the surfaces of contact. So I'll use the shorthand notation for perpendicular. The surfaces of contact. So right now you are sitting in your chairs, there's a normal force between you and the chair. It is perpendicular to that surface of contact. Well, we're going to assume flat chair just to simplify it. So the chair is pushing up on you and you are pushing down on the chair. It's what keeps one object from going through another. Right now there's a normal force acting on my feet, keeps me from falling through the floor. As implied, if you are pushing down on the chair, and the chair is pushing up on you, those forces, pardon? Yes, push away. So with respect to each other, they point in opposite directions. So, on different objects. Since forces come in pairs, when I draw a normal force, I know there's going to be a second one, and the second one will be pointing away from the other object. So perpendicular surfaces of contact, and I'll leave it like that. All right. Weight. Questions on normal force before we talk about weight? All right. Weight. Tell me something about weight. Besides, the symbol for weight is lowercase w. Okay. So with respect to the objects, it is towards center of mass.
Each other, 20 points for each other.
Other object. And what I mean by other object is that there's a gravitational pull between me and the Earth. The force acting on me is towards the center of the Earth. The force on the Earth is towards the center of mass of me. I'm pulling up on the Earth is pulling down on me.
And then the requirement for just weight is going to be one small mass, one huge mass.
Yep.
And then for the general mass, it should be two masses.
There's one other thing with one small mass, one huge mass. I am a small mass. The sun is a huge mass, but the force between me and the sun is not considered weight. That would be still gravitational force. What would need to be required in order for the force between me and the sun to be considered weight? Yeah. So one small mass near one huge mass. And small is small in the scale of basic, planets, moons. An elephant is considered small in this context. All right. Attention. Or questions about weight or gravitational force in general? Attention. Sorry? The requirement is that not just a rope or chain, it is a pulling force, a tight or taut rope or chain. Rope, chain, string, whatever you happen to be using. the AUT. It is a pulling force. So with respect to each other, they're pointing towards each other. Tension in some sense is opposite of normal, because normal is a force that pushes things away. Weight and tension, or gravitational force and tension, pull things together. And then the direction with respect to the objects. And friction.
It's gonna be parallel to like surfaces, but it's gonna oppose desired relative motion.
Surfaces of contact. And just a word on the desired relative motion. If I push on this table right here, if the floor were frictionless, the table would slide that way. So it desires to move that direction. Therefore, friction on the table is acting opposite that. As I move to the left, to my left, the marker is moving with the paper. Now, I don't have any Jedi powers here, so I am not causing the marker to move. It's the paper that is, but more specifically, the friction from the paper. The desired relative motion is, if this were frictionless, the marker would stand still as I pull the paper out from underneath it. So the marker, the desired relative motion is the marker wants to move that way on the paper, therefore the paper acts that way on the marker. With respect to each other, technically they're all anti-parallel, but this one they're just sort of lined up like that as opposed to really pointing towards each other. And the requirement for friction? Say that again?
Desire and relative motion.
There was the conjunction in there that I might have misheard. Like that and. I don't know if you said it more. And that's motion relative to what it's touching. And other, or other that we skipped. Listen to that.
On the video, it said something about friction also being considered as a normal force. I just put parentheses next to it.
It's that friction or tension?
Friction.
Oh, sorry. It requires normal force. Okay. Yeah, that goes along with contact here. So if there's contact, there is the normal force, there might be friction. But you cannot have friction between objects that are not touching. So I'll throw in normal force here. It is a requirement, it is necessary, not sufficient. Between objects. There we go. If I want to what? Oh, this is a question about.
If you're going to state that not on the top.
Well, for the force diagram problem, I'll put in all the objects that you need to draw forces involving. For a problem that is not just a straight up do the force diagram, it depends on the problem. Was that sufficient? Other questions? All right. Let's actually apply it. So those who've seen the video, no doubt you're excited by seeing box on ground. I'm going to skip the box falling. It's in the video. But box on ground. All right. So when you're doing force diagrams, one of the things is you need to draw the objects separately. Do not do a force diagram with the original problem. If you see hatch marks like that, that means you have an object that you're considering fixed. So it's on the ground is not moving. So I draw my two objects. I am not claiming the boxes in the air. I'm just claiming that I've got a box and I've got the ground, and these are where I'm drawing my forces. And then I go down the checklist. Also, as stated in the video, if it looks like it's meant to be flat, it's flat. I'm not going to put a 1 degree angle in there. I can't believe you missed it. No, if it looks like it's supposed to be flat, it's flat. And if in doubt, ask. Not that one. That one. All right, let's go down our checklist. F down. Is there any friction involved here?
No.
Why not?
It's in one place.
No.
Well, no.
It's not. You know, when I was pushing on the table right here, or that table, but if I push on that table is not moving, but there's still friction involved. Why is there no friction?
There's no desired relative motion.
Yeah. If the ground were frictionless, that box is not going to slide. So, no friction. Tension.
No.
Why not? Yeah. That requirement's not there. Other?
No.
Why not?
There's no other forces acting.
How do you know if there's another force? And other force.
What did you state it?
Probably. Yeah, the other shows up. Textbook problems are great for other forces. Where you have a 5 Newton force pushing on a 3 kilogram box. Oh, like the examples I did in class last week. Those are other forces. Weight.
Yeah.
Why? Why do we know that there's weight involved? So for what's the requirement? Yeah. We assume that the ground is part of a huge planet as opposed to somehow this chunk of sod is out in the middle of nowhere. This is part of the planet here. So it is a gravitational pull. I have weight. I have weight. Yeah. That's the way you would label it. And a normal force. Is there a normal force?
Yes.
Which way is the normal force acting on the box? So if the normal force is acting up on the box, that's what I'm drawing my arrow. I'm going to draw my arrow up on the box. And there you go. It's not something known as a free body diagram. Free body diagram looks very much like this, except they take the box and they represent it by a point. Box. And they draw an arrow up. So they draw an arrow down. And that's the free body diagram. I'm really not a big fan of that because that will become an issue in chapter 8.
Free body diagram, and you have multiple arrows going each way, and you do it side by side. Extend the dot, or just do it side by side?
And I can just do it side by side if it's understood that it's all coming from the same object. Unless you cram everything together. Any other questions? All right, the next exciting installment is
Box on ground.
you bet. So first thing is I draw my picture of what's going on. I call that box A and box B cleverly, and that's ground. So what's the first thing I do? Now I recommend that you draw the objects in the relative orientation. Since A is above B above the ground here, I'm going to draw it so A is above B above the ground. It doesn't officially have to be, but it just makes life a little bit easier for visualization. Put down our checklist. What can we eliminate? For the exact same reasons as over there. It's all level, there's no reason for any of these things to slide if anything were frictionless. There's no rope or string or pulling on it, and I didn't introduce any mysterious thing in the problem. All right, weight. Is there any weight involved?
Yes.
Acting on? Which way is it acting on A?
Down. Subscript.
What is this force between? It's between A and the ground. So the other part of that, since forces come in pairs, on the ground. Now we need the subscripts because we have two objects, so we're going to have two different weights there. Two small objects will have two different weights, and we need to distinguish between them. So as implied. So those are the forces that are acting downwards. Weight is the force that does not require contact between the objects. Yeah, all the ones over there. Do not draw weight of A up on B as the second part of that force. If W sub A were here, this is not correct. So you don't want to write down unless you make some difference there. If this is true, that means if box B disappeared, A would just stay there. But if B disappeared, A is going to fall because that force is with the ground. All right, so weight is done. Normal force. Where is it going on A? And on B? If they have the same subscript. Now, I typically do a subscript that has some meaning to what's going on here. That's box A, so I did a subscript A. It doesn't have to be an A. I could have done 1 and 2, or just so long as it differentiates. For example, with a weight, I need to somehow differentiate between these two weights, so the subscripts just need to be different. Done. Force diagram done. All right, so let's actually do a real application of this, of that last one. Just one kind of marker. All right, first is on a scale on the ground. Thank you. Thank you. All right, so we're doing a force diagram here. So I got person, I got scale, I got the ground. Just as before, we have only weight and normal force. What are the forces acting on the person? Give me directions.
Weight is pointing down with subscript P.
Whatever subscript you like. Did you say P or B? P. Okay.
And then Y going up on the body.
Where's the other part of this pair, of this weight?
On the ground.
Yep. And the other part of the normal force?
The scale.
Okay.
And then on the scale, you're going to have normal Y X going up, and then Y X going down on the ground. And then you're going to have W X going down, and then W X going up on the ground.
It should look pretty much identical to what we have over here, other than the subscripts. Now, obviously, some of you have seen the video, so I'd like you to sort of hold on for just a moment, let the other people try to answer this. What does a scale actually measure? Okay. Hoping for those that have not seen it yet. Why normal force? Why is she saying that the normal force is what a scale measures? And not your weight? Don't they?
Normal force is the amount of force pushing back up on you from how much you weigh. Sort of, depending on how much you weigh, causes a certain amount of normal or support force to come back up from the ground or wherever you're standing on. So a scale would measure that.
Okay. There are situations where that's not the case. But when we look at, in terms of the force diagram, what you're telling about the weight of the person relative to the scale.
Can you repeat the question?
What can you tell me about the weight of the person with respect to the scale? Think about the forces acting on the scale itself. Where does the weight of the person show up? That's the weight of the person. Where does the weight of the person show up here? The scale does not feel the weight of the person at all. What force does the person exert on the scale? This one right here. That's the only force the person exerts on the scale. Now going to what Dulce was saying, if he is in equilibrium, let's connect back to what we did last week. If person is in equilibrium, the total force on him is 0, which means that the forces up have to equal the forces down. So the normal force acting on the person from the scale, which is the same magnitude as the force that the scale exerts, that the person exerts on the scale, would be equal to the weight of the person. So if he's in equilibrium, those two are equal. This goes back to what Dulce was saying. What's a situation in which the normal force is not equal to the weight?
Is it whenever they're jumping up and down? Still?
Yeah. If you're bouncing up and down on the analog scale and you see that needle goes shooting back and forth, or the dial underneath shooting back and forth, your weight is not changing. I don't weigh 500 pounds when I step on the scale just because the needle shoots over to 500. When I'm bouncing on the scale, this normal force is changing, and the scale reflects that. Questions to hear?
So, I think in the video was a weight on top of the scale. When it hits the ground, it bounced from 20 pounds to like 80 pounds. What would be like the explanation of that? Would it be just a greater force acting on it?
All right, so if I drop an object, it's going to stop when it hits the ground. And the force to stop it has to be much greater than the weight. So part of this will connect with chapter 3, but if he is falling, if this person or the weight is falling and it's stopping, that means that the total force has to be upwards. So we have the difference between them. So the force up minus the force down is equal to mass times acceleration. This is Newton's second law, chapter 4. And so depending on what the acceleration is, that will affect the difference between these two. So your weight is, given the way we've written it, this weight is some number for being around 215 pounds. And so when I stop suddenly, my acceleration would be upwards. So it would be positive because I made that positive. I should just go ahead and say this positive. So stick some numbers in. Let's go metric. So my weight is around 1,000 newtons. My mass is around 100 newtons. Sorry, 100 kilograms. So if I'm stopping suddenly, my acceleration will just say 20 meters per second squared. And so the normal force, what my legs are going to feel, is going to be 1,000 plus this, or 3,000 newtons. So in the case of the video where the mass is falling, the weight's different and the mass is different, the acceleration will be different, but it's still that this is going to have to be bigger than that. Yeah, that and a bunch of other similar type things that scale it. It will show relative weight, but it doesn't give accurate weight anymore. Yes.
So if you're moving up and down, your bottom motion is greater than you stay up.
Right, because if I'm hitting a peak right before I come back down, when I'm hitting a peak, I'm accelerating downwards. And some of the language will get into more detail in chapter 3. But as I'm slowing down and then I speed up coming down, my acceleration is negative, so the downward force is bigger than the normal force. So therefore the normal force is less than the weight, so that's why the scale will read less than. But as I'm coming down and then bouncing back up again, my acceleration is upwards. So the normal force has to be the bigger one. Is that good enough? Other questions? Let's put it away. Of course, we're doing box on ramp. Now I don't have a connection, I don't have an extra line here, I'm just saying that the ramp is part of the ground. And they got a box on it. First thing, draw them separately. Now some people like drawing, they straighten out the box, they reorient it, but I recommend against that. It's not inherently wrong, but the students who straighten out the box tend to make a fundamental error in one of the forces. All right, we got a checklist. Where do you want to begin? There's friction? How do you know there's friction?
Because the box is moving down, so you got the surfaces and moving the box down.
Okay. So the box wants to slide down. There's the desired motion of the box down the rim. So which way is friction acting on the box?
In opposite direction.
All right. So I got some friction acting here, but forces come in pairs. So I got another one somewhere. Yep. This should be down the rim.
I thought we put the direction where the box goes first, and then second arrow where friction acts.
Going that way. Friction opposes the desired motion. Since this wants to go down the hill, friction opposes that by going up the hill.
The first arrow shows where actually the box goes, and second.
Now, this is the force that the ground exerts on the box. This is what the ground is doing to the box. This is what the box is doing to the ground. Did I address your question? Did I? Okay. Friction done. I have only two objects, so I can only have one pair of friction there. That was a bad reason why. There's only one point of contact, or one place of contact, so therefore there's only one pair of friction. All right. Okay. Okay. Down, by definition, is the direction of the gravitational pull. So there is a force downwards. Now, where I draw up, sometimes I'll draw it, sort of right where the box is. Sometimes I'll draw it off to the side. It doesn't really matter. This is all one object. There's this weight pulling up. The weight of the box is pulling up on the ground. This is probably the biggest mistake that students will make on this type problem. Got to remember normal force. Normal means perpendicular. Normal force is perpendicular to the rim. Normal force and the friction associated with it will be perpendicular to each other. Questions here before I extend this slightly? All right. So let's say the box is sliding in dynamic equilibrium. What does dynamic mean?
Changing.
What's changing? Say it again? Yeah, it's changing position. It's just moving. So this just means it's moving. And equilibrium? What are the three things that are true if something's in equilibrium? Say it again? Yes, there is. It is dynamic, so it is moving. But what about velocity? Yes. Change in velocity is 0. All right, so if it's in equilibrium, the key thing that we care about in this problem is that the total force is 0. Well, if the total force is 0, we're going to add them head to tail. So I got weight acting down. I got normal force acting up at that angle right there, perpendicular to my ramp. So somewhere along that line right there, that's supposed to be parallel to this y perpendicular to that ramp. And friction is acting perpendicular to this. And since it's an equilibrium, the total force is 0, I need to end up exactly where I started. So I know y can't be this big because I can't connect them. So I need to connect it. So that's going to be my friction, and that's my normal force. And that is not needed. So the total force being 0 means that when I add them together, I end up back where I started. If it were not in equilibrium, so just sliding down and getting faster as it goes, well, I know direction of acceleration is down the ramp. And so if it were not in equilibrium, then weight is still acting down, normal force is still acting that direction, and friction is acting back this way, but it won't reach there. And this little bit, that is the total force. And because that total force is not 0 in length, it is accelerating. And there's a lab we probably will not do. There's a lab where you would actually go through this and try to figure out what the acceleration is based upon, or what the friction is based upon the length of the arrows. Questions to hear? Todd?
So tell us if it's in dynamic equilibrium, or will we figure that out?
Most of the problems I tell you, whether it's an equilibrium or it gives some clue, there's one problem where I said it's moving at a constant velocity, which you should interpret as, oh, it's equilibrium.
Because dynamic equilibrium would be especially, like it would not be normal because normally things are going down.
Okay. A lot of things accelerate when they go downhill, but it is possible. I mean, I've been in cars, I've driven in cars where I'm going down a slope, foot off the gas pedal, and my speed does not seem to be changing at all. And my direction doesn't change much either. Just because I drive cheap cars and there's a lot of friction there.
Well, because your acceleration due to gravity.
Acceleration due to gravity is the acceleration when that term acceleration due to gravity refers to acceleration in free fall. If something is falling and there's no other forces acting on it, just the weight. Did I jump to a conclusion about what you were asking?
I think you answered the question in that.
Okay. Did you have a follow-up question?
Maybe eventually I'll figure it out.
Okay. gotta have one with tension in there, and then we get to the test level problem, one that, for which I don't think I've done any video. Let's make it a little bit more extensive. Yeah. Probably too extreme. That way. And I'll call it literally A, B, C, and D. So I have 4 masses, I got a bunch of pulleys, I got some ropes. I have 3 ropes. There's a more intermediate step in the videos that you can watch. But now, when given a more complex problem, knowing how it's divided, for instance, is the pulley different than the ground? Should you do the forces between the pulley and the ground? That's going to depend upon what is necessary. Badly worded. I would let you know whether what needs to be included with what on the test level problem. So on this one, I would, there's A, and because I'm drawing the ground with the pulleys attached to it, I'm indicating that I'm considering the pulley as part of the ground. I've got B, C, and D. And then I have a rope. A little bit of detail about the ropes. Ideal rope. For those who've seen the video, what's an ideal rope?
Frictionless, massless, and stretchless.
And ideal pulley. What's an ideal pulley?
Massless and frictionless.
And we pretty much keep that for the duration of this course. Physics 151 and 251, we would do away with the massless, frictionless aspects here. And 251, potentially we would do away with the massless rope. And stretchless, we don't really get into 251. That's the calculus space version of this. Got the checklist again. Let's hit the easy one. Other. Let's say what I consider the next easiest one, weight. There is weight acting on the ground. Up from the ground?
Down from each of the boxes.
Okay. Down on each of the boxes. So I got W sub A, and then up here, W sub A, W sub B, W sub B, W sub C, W sub C, W sub D, W sub D. All right, weight done. Normal?
Down.
Okay. There's got to be something holding this up because it is in free fall. So there is that weight acting up. Or sorry, that normal force acting up. sub A, y sub A. What's the direction of the normal force on B?
It's going to be perpendicular to the slope of the wave.
Y sub C, y sub C, and y sub D. Is there a normal force on D?
No.
So I got an up and a no.
Is it wrong? It's kind of so it's not so.
There's no normal force here because the only thing that's touching is the rope, and we're going to call that force tension. So normal force done. Let's do friction next. On which objects will there be friction? Always frictionless. Okay. So A, the friction is, well, A wants to go that way relative to the ground, so the ground's trying to hold it back. And then there's FA here. B wants to slide down. C wants to slide that way. Okay, FC. FC. And there's no normal force on D, so there can't be any friction. It's not sliding against anything. And lastly, tension. Tension exists wherever I've got a rope. I got 3 ropes, so I'm going to have 3 sets of tension. Tension is a pulling force. So I'm going to have a tension at each end of the ropes and then whatever it's connected to. So I got a tension here called FTA. FTA. I got tension here. Oh, we are not done with normal force, by the way. There's 3 more. So FTB. FTB. It's being pulled this way. FT3. FT3. FTC. F. Getting really crowded there. Not give myself enough room. That's a rookie mistake. FTC. FT4. FT4. FTE. So I'm going to have a friction point on each end of the rope, and then whatever it's touching is going to be the counter force. So I've got FTD and FTD, FT4, FT4. However, we could simplify this a little bit. In an ideal rope, and I will tell you the force diagram problem on the first test, it will be an ideal rope. The tension is going to be the same throughout. If it's frictionless and massless and stretchless, these tensions are the same, so I don't have to use different subscripts here. I could just call this all FTA. Call this FT3. And those would be the same, so I'll make that FTD. So for an ideal rope, I would have the same tension on each end. Which is why when we were in the hallway and we talked about the tension there, that the tension that I think it was Ty and Elizabeth and were exerting, it was pretty much the same tension on each end. It was not an ideal rope, but it was close enough. Questions here before we hit the last 3 normal forces that we ignored? All right. What are the normal forces we ignored?
Contact with the boxes in the rope.
No, that's tension.
Between the pulleys and rope?
Yes. I assume that's what you're about to say. Because the ropes at a tilt on it this way. So this would be F, sorry, no, Y R1. YR1. Now, I don't know the exact direction of this. I didn't give enough information, but it's somewhere in that range. Get close enough. These just need to be in opposite directions. Here, the road is being pulled this way, so FT2. And here, it's being pulled this way. F. I'm sorry, Y, not F. Wow, that should be Y2. Y3. And not intended, but I'm also illustrating the problem if you don't give yourself enough space. There are classic mistakes that you'll see when you watch the videos. There are other classic mistakes. Questions? All right, when we take 5, I'll set up the test level problem and we will extend the excitement. All right, we're recording again. This is the problem. This would be a test level problem right here. And you'd be asked to, it would probably be a paragraph explaining the scenario, but then you'd be asked to do the course diagram, usually on the next page. And so on the next page, you would see it broken up into the parts of that matter. Something like that. I'm going to give myself some more space here.
Is the box attached to a road? Is the road attached to the car?
The box, the road is attached to the box, which is sitting in the trunk, or sitting on the back of the truck or car, whatever that is. Going around a little bit.
And the not slipping, I assume means he's not slipping off the station.
Oh, right. Yeah, he is not slipping off.
He is not coming off the board, rather
Right.
the board is moving.
The board is indeed slipping on the road.
I thought that it was pointing at the person.
Yes,
Yep,
that was the intent.
What is the arrow pointing towards the human?
This right here. Any money. Key money.
That's what I thought.
And Garage is the most common misspelling of my name. I had a bank card for Garage Box for a while.
everyone does, oh, that's not my name, it's spelled incorrect.
I still used it. I was amused.
My sister's name is Callie, K, so if you spell it with a C, she'll get real offended, because that's not totally not her name. So for the entire time, for months on end, one of her teachers would, anytime he was writing something for Callie, he'd always do it with a C. Constantly.
One of the tutors today called me Elizabethan.
Because you're graceful, you're queen line. Okay. All right, let's do it. Let's do friction last. So let's. Can we get rid of anything?
Other.
Yep. Okay. Besides friction, what do you want to do first? All right. So, what objects are going to have weight? Or what objects won't? Yes. Which way does weight act on the smaller objects? Which way does weight act on these objects? Yes. No matter what else is going on, we can be sure of that one. So I got weight of Gerouge, and then weight of Gerouge. I have weight of sled. There we go. Weight of sled. Rope, I'm going to ignore. It's ideal. Weight of box. Weight of box. Weight of, I'm going to call it truck. Weight of truck. Weight of chair. Weight of chair. And then weight of e-money. Weight of if you do put a weight on the rope, and then another one up coming up from the ground, I don't take all for it. I just circle it and I write ignore, although it doesn't always. Ignore written sort of like something like that. So there's no penalty for it. It's just I'm acknowledging that it's there. That's it. Those are all the weights. What next?
Normal.
Okay. Between what and what?
The ground and each object. Each object is going to be fixed up except for the rope.
Too generalized. Was that Emily? It's. If you said something.
I said all objects except for the rope, the box, and the chair. And the person.
The normal forces will tell those.
All objects and the things that they're touching. So, for example, there's a normal force in between the person and the sled. There's a normal force in between the box and the truck, the chair and the truck, Eddie and the chair, and then the truck and the ground.
Yeah, there are a couple that you missed in there, but that, so far so good. What I heard Elizabeth, I want to say Elizabeth Ann is you said normal force between everything and the ground, and not everything touches the ground. So there's a need between Gerouge, and the sled. So y sub g, y sub g. And again, you don't have to use the same subscript that I do. I usually, because it's a sled, I could have done y sub s here, but I tend to start at the top and work my way down, so that's why I start with the g. Then sled and ground. Y sub s. Y sub s. I know the box has something holding it up because otherwise it would be falling down. Why is it B? Why is it B? And then, so if I mention Eddie in the chair, why is it B? Why is it B? And then chair and truck. Why is it chair? Why is it chair? And then you mention truck and ground. All right. So we have 2 points of contact with the ground here. I don't need to draw a set of normal force here and a set of normal force there. Because if you're going to draw 2 normal forces, well, if it's a typical vehicle, it's got 4 wheels, so why not draw 4 of them? Maybe it's a dually and it's got 6 wheels. Maybe I should draw 6 of them. Or to simplify it, there's a normal force between the truck and the ground. I'm just going to draw 1 arrow to sort of encapsulate all the normal forces. White truck. White truck. So there are only 2 things touching the ground, so therefore only 2 normal forces down on the ground. Did I miss any pair? We got that. I think I'm good. How's he holding on to it? If he's just holding on like that, so if he's holding on like this, then that would be a friction force. If it's wrapped around his hand, then there's probably a normal force in there too. Because we don't know, I didn't give you that kind of information, then we're just going to bundle all that up into tension. Yes, there will. All right, so tensions. So I've got a tension, well, I've got a rope here, so I've got a tension pulling on each end. And this is attached to the box. And this is attached to the person. Plug this thing. I can't tell. And now we're left with friction. Friction is probably the hardest one, where most mistakes happen for people who get this far. Now remember, there has to be a normal force wherever there's friction. Normal force is a requirement for friction to exist. Just because there's normal force does not mean there is friction. But if there is friction, there has to be a normal force. So at least that narrows down where we're looking. So there's a normal force between sled and ground, and so therefore, I know there possibly is a friction here. Is the sled, does it have desired relative motion relative to the ground? Yes. Which way is the sled going relative to the ground? And therefore, which way is friction acting on the sled? So the ground is trying to slow the sled down, and the sled is basically raking the ground. All right. One down.
There's friction in between George and the sled because the sled isn't directly being pulled. George is being pulled, but he's pulling the sled underneath, so there's friction between those 2.
Another reason why we know there has to be another force here is that I said the acceleration is that way. They're all accelerating together in that direction. The total force has to be in the direction of acceleration. Has to. I have no forces acting to the right, so there's got to be something acting to the right. And so it's indeed friction. Or from the point of view of relative motion, if the sled were frictionless, or its feet were frictionless, Guerrero should be sliding that way. So his desired movement is that direction relative to the sled. So therefore the sled is trying to oppose that. And this is the force that's causing the sled to accelerate to the right. Two down.
Alright, now it's gonna get a little bit tricky here.
Let's do car and ground at the end. Let's do that one last. Because there is something I deliberately put in here to make it that one a little bit more difficult. All right, box and car. Which way is the friction acting on the box? Wait, label it. Which way are you pointing? Pointing that way? Okay.
Actually, who's it on this cell? God was there, but he would like it should be moved to both directions.
If this were frictionless in between these two, which way would the box go relative to the car? Yeah. So there's got to be the friction is acting this way. And all right, so another one down. We've got 1, 2, 3 more normal force pairs where there might be friction. Okay. Which way is friction acting on the chair?
Back.
Right. All right. What? All right. So you said that way, and you said that way. Okay. And you're going that way also.
Since the variable direction is that probably that.
If there were no friction between the chair and the and here, oh, there's one more normal force pair that we missed. If there were no friction here, what would happen to the chair? Right. Therefore, which way is friction acting on the chair? Also, if the chair is accelerating in that way, there's got to be some force in that direction. FC and then FC. All right. Now we got E-money and the chair. There's a little bit of information I do need to give. Let's assume
I'll translate this in a second.
okay. E-money is pulling the drive rod, that's what this shaft right here is that's attached to the vehicle, straight toward himself, parallel to the ground. So he's pulling on this rod towards himself. All right, so I'm going to go ahead and take care of that normal force. He is touching that rod, so there is a normal force there. Which way is the normal force acting on him? The meter stick. So like this, and he's pulling straight towards himself, pulling in that direction. Which way is the normal force? I guess this is going to be in opposite direction. Which way is the normal force on the rod? All right, so I've seen all sorts of different directions there. I've gotten that way, and that way.
It's
Not his arm.
the stick.
Did you say his arm first time? Okay, no, it's not the arm, not covered. That's what you meant by the car. The stick. You're right. So as it's going this way, there is a normal force perpendicular to that rod. So it's pulling, other direction. So it's pulling on the rod that way, pulling on his hand that way. Normal force I was using blue. So there is a normal force in that direction. I call it, I don't think I'm using R anymore. And then Y is the bar. This is one of those things that when I come up with my grading sheet, and I'm starting to grade it, and let's say that I left that out because it was a moment. And then I see somebody who's actually put it in there, and I think, oh, I can't believe I missed it. And then I go back and I grade all the other ones that I missed before. Presumably they left it out also. All right, so we got the normal force there. Okay, friction. So we got friction between chair and truck. E-money and chair. Which way is friction acting on him?
Would it be right?
So I got two to the right. And you're going to the left. It's going to be one of those. Got another one to the left, or are you just still thinking? Got another to the right. Take another moment for people to come up with settle on an answer.
I guess technically there wouldn't need to be a friction between. Well, you could also theoretically say that there's a normal force in between his back and the back of the chair, which could be right where.
Deliberately don't have his back.
Oh, okay.
If his back had been on the chair, then yes, there would have been another force there. That makes it even more difficult. All right, so the friction on E-money from the chair. Who says that way? So that's you're right. So that was just one person now satisfied with that? 2, 3. All right, to the left, 4. Okay, who says going to the left? People are not really willing to just sort of put themselves out there. Because you're afraid you'll make a mistake. Shouldn't be afraid. You'll make plenty of mistakes. We all. All right. It really depends on how hard he's pulling on that stick. If he's pulling really hard on that stick, he's going to be pulling himself forward, and so friction will be acting back. If he's just barely touching it, then the friction is going to be in that direction. So it actually goes either way. That's a situation where, in my mind, I was thinking that the friction acting on him would be in that direction, but there is an argument for it being the other way. So, just for the sake of this, I'm going to put it that way. But it could possibly be in the other direction if it's not.
So for the sake of a test, would you state which, like, how fast he's going to, like, gaining enough force to jerk?
I would, if I catch it before I give the test, then yeah, I would add another sentence in there, eliminating that one. If you look at the MacGyver test, I'm actually not sure if I posted it or not, but there's a MacGyver problem where I throw in 2 extra sentences to eliminate any doubt about which way the friction would All right, what about friction between his hand and the rod? Again, rod's like this. He's pulling towards himself. Which is the way when his hands slide on the rod. So which way is friction acting on his hand? So the friction on his hand would be down. F sub R and then F sub R. And I think now we've done everything except for truck and ground. I'm going to grab the wheel from next door, and then we'll talk about the wheels. All right, so we have the wheels. We have the wheel. What is meant by front wheel drive?
That the front wheel is the one that powers and the back wheels are not under
Okay.
power from the engine.
If this thing were stuck on ice, perfectly frictionless ice, and the person got it to accelerate in that direction, this wheel would just spin, this wheel wouldn't move. So one is going to move because of the engine, the other one's going to move because of the ground. So front wheel drive, this will move because of the engine, as Ty said, this one will not. Which way is this wheel going to turn? So let's see. So choices are, from our point of view out here, clockwise or counterclockwise. So, oops. What if I not draw like that? So we've got, so those are our two choices right there. So counterclockwise before, anyone say clockwise? Looks like we got a lot more clockwise. If this thing is being dragged along, so I'm going to put my hand here on the axle. If I'm accelerating that direction, the wheel's turning that way. So that was clockwise. What's causing it to turn that way? I think I heard two people say it. No, not directly. From, yes. The ground is causing the friction here. So the friction is getting the wheel to spin in that direction. So which way is the friction acting on the wheel? So there's a friction acting here on the wheel. But F W1 or R for rear. The front wheel drive. Putting it in the language that we dealt with before, if the back wheel were on ice or something frictionless, it would just be going like this. So the desired motion against the round is that way for the bottom of the wheel. So friction acts the other direction. Now the front wheel. The front wheel is being powered by the engine. So that would be as if I'm turning from here, not from here. Which way does the wheel want to go relative to the ground? The point of contact.
It wants to go to the left.
The friction is acting that way? That, from your point of view, that is left. And friction is acting to the left. on the front wheel. What is, I said it's accelerating that way, so there's got to be some force in that direction. What force do we have in that direction that makes the truck accelerate that way? Engine, only thing the engine really affects is the wheel. And air quality. Because the engine is driving this. So you get some sense of which way the wheel is pushing it. If I turn the wheel from some, I'm externally causing the, or internally causing the wheel to turn. It's pushing that way. That's the ground. It's pushing the ground in that direction. Therefore, which way is the ground pushing on the wheel? Oh, whoops. Better. Questions about this?
If we ever have a vehicle question, are you gonna state if it's all wheel or?
Yes. I usually make it all wheel, but I decided to do something special here. And this, the complex, the test level problem, this is a test level problem. Their test problem will not be this one. But something of this type most likely will be the next to the last question on the first test.
And like with the master instead, you would break apart
Yes.
the images that so that we don't have to guess whether the box and the truck are connected. You would indicate that
Absolutely.
are or are not.
Yeah.
By breaking it apart.
Because if I don't break it apart, then yeah, you can only consider we've got a box and a truck, so they separate or apart, but you could also go top of box, bottom of box. Upper left quadrant, upper right quadrant. I mean, you could break the box up down to the atomic level if you wanted to. And that is the path to madness. I don't recommend it. Questions to hear? All right. Let's take a break here, stretch your legs. I'm going to try to set up and see if I can actually project something from this. While I'm going about that, let me pause. Okay, well, I didn't record any of that stuff. So here we go. All right, so the next term, displacement. There's basically two ways of looking at this, depending on which one is more convenient. There is where an object is with respect to the starting point, or change in position. There's another aspect to the vocabulary. When I say displacement, I'm talking about overall displacement. So my default is overall, as opposed to instantaneous displacement. So if I want instantaneous displacement, in other words, where am I relative to where I just was, I would need to say instantaneous. But if I just say displacement, I'm talking overall. So it must specify instantaneous. Now there is a scalar analog to that. So if you see the word displacement, you should be thinking vector, And you see position, vector, the scalar analog of displacement is called distance. Basically, how far it's traveled. So let's say that this is Columbia, South Carolina, Winston-Salem, North Carolina. That's about 200 miles. Ish. We'll just say 200 miles. If I go from Columbia to Winston-Salem, of course it's not a straight road. They didn't design roads that way for the most part. You know, you meander. You decide to see some scenic places. Then you eventually end up in Winston-Salem. So the odometer in the car had registers 500 miles. What was the distance traveled? Yes. What was the displacement?
I need more. 200 miles.
I need more. There we go. As a group, we got it. So my displacement was 200 miles north. My distance traveled was 500 miles. All that the vector cares about, displacement cares about, is where am I relative to where I started. It doesn't care about anything that happened in the middle. The symbol for displacement is you just put a delta in front of whatever you're using for position. This delta right here means change. The symbol for distance looks a whole lot like this, except you drop the vector symbol. Whatever letter you have to be using, bless you. So over here, delta x is equal to 500 miles. Delta x with the vector symbol, 200 miles north. Or if you don't feel like writing that much, if it's a one-dimensional problem, you could just say that, well, that's the positive direction, and just write positive 200 miles. It's my displacement. All right. So there's a little exercise that we're going to do. That is going to be 0 right there. It's going to be a one-dimensional problem. I'm just going to be moving back and forth. I'm saying 0 is right there. And I'm going to make that is my starting point. And I am going to define to the right as positive. And apparently, something happened. All right. Oh. So right now, assuming again, my starting point was here, and I'm now here. My position is positive, negative, or 0? Yes, because I'm on the plus side of 0 over there. Is my displacement positive, negative, or 0? I think somebody just said it. Yes, that's the way it's played. All right, right now, my position, positive, negative, 0. Because I'm on the plus side of 0. My displacement, because I'm on the negative side of my starting point. My position, displacement, and that's the way the game is played. Questions up to here before we make it more complicated? Velocity. Velocity is a vector. The symbol for velocity, v with a vector symbol over it. It is the time rate of change of position. That's just the fancy way of saying it's the displacement divided by however much time it took me to get there. Or it is how fast and in what direction an object is moving. By default, if I'm asking you for the velocity, I'm asking for the instantaneous. This is the default. As opposed to the average. So if I want the average velocity, I need to specify average. So over here, I did this trip, and let's say that the trip happened in 10 hours. What is my average displacement? Sorry, try that one again. What's my average velocity? The average. Keep going. Keep going. Yes, there we go. 20 miles per hour north. From the formula that I wrote over there, it's the displacement. So this is equal to my displacement, which is 200 miles north, divided by the amount of time it took me to get there, which was 10 hours. There's the math problem right there, 200 divided by 10. And then the rest of the stuff, we just, units and direction. My velocity is positive when I'm going in the positive direction. It's negative when I'm going in the negative direction. Doesn't matter about where I am, just matters which way I'm going. It's the how fast and in what direction. So right now, my velocity now. All right, we're gonna need faster responses because I got three things going on here. Position, displacement, velocity.
0.
Yep, there we go. All right, position, displacement, velocity. I think I heard somebody say 0. Okay. My position, my velocity, my displacement, my position, velocity. Okay. And now the hardest one. Oh, this one over here. There is a scalar equivalent or analog of it. Anybody know what it is? So, yes, speed. Police catch you for speeding, not for velocity. Yeah, if they start putting velocity in there, they'd have to get, the angle of the road. Northeast, 50 miles per hour. The symbol for speed is a V without the vector symbol. This really stumps some students because they see V and they think velocity. It's not. The velocity is a vector, so if I do this, the shorthand with just the V, there's a vector symbol over it. The math formula for speed is just distance over time. So over here, what is the average speed?
20
Nope. Yes. Distance. So it's 500. Wow, it looks like 800. 500 over 10, that's 500 miles over 10 hours, 50 miles per hour. So there's a very clear difference between the two. So let's just say, for example, again, before we get to the hard one, I'm racing the same Bolt around a track. Let's just say 400 meters all the way around the track. Usain Bolt does it in 30 seconds. It's Usain Bolt. I do it all the way around the track in 300 seconds. What is Usain Bolt's average velocity when he gets to the finish line? Usain Bolt's average velocity when he gets to the finish line. What's his displacement when he gets to the finish line? Yeah, it's known. He's exactly where he started. Therefore, what's his average velocity? Meters per second, and it's 0, so whatever direction you want. I get around to the end also. What's my average velocity? Let's go with units.
meters per second.
Yep. So in terms of average velocity, I'm as fast as Usain Bolt. Now let's take it one step further. When he finishes, he has gone nowhere in 30 seconds. Whereas I am here in 30 seconds. I have a non-zero velocity because I've gone somewhere. He hasn't. I'm faster than Usain Bolt. After 30 seconds, I've gone somewhere. Now, if you want to spoil it, you can start looking at the speed, but I'm not, because I don't want to spoil it. All right. Now the hard one. Acceleration. Anyone want to take a wild guess what the symbol is? With a vector symbol. So A with a vector sign over. The scalar analog, unfortunately, is acceleration. And then symbolized by the A without the vector symbol. I've gotten better about this. Occasionally I might slip up, but just be aware that after I use the word acceleration, I try to put either A with a vector symbol or A without it, just so you know which one I'm talking about. Textbooks don't do that. Typically, this is the one that the textbooks mean is the vector one. It is, if I don't specify, we're talking about instantaneous. And if I want the average acceleration, I need to specify average. And all acceleration is the change, is the rate at which velocity changes. So time rate of change. Of velocity. Which mathematically is just the change in velocity over the change in time. So we talked about velocity, now we're talking about change in velocity. if you're driving an automatic transmission vehicle, from a physics point of view, what are the 3 accelerators that you have easy access to as a driver? There's 1, 2, yes, and the gas pedal. Gas pedal speeds you up, so there's change in speed, therefore change in velocity. Brake slows you down, change in speed, therefore change in velocity. Steering wheel changes direction, therefore you're changing velocity. Brilliant, or you just didn't see the answer somewhere? Brilliant. All right. Go with that. So acceleration doesn't care about how fast you are going, it cares about how your velocity changes. So if I start out slowly and then I speed up, I've accelerated. So my velocity is positive, and then it's more positive. So my change is positive. If I went from 5 meters per second that way to 10 meters per second that way, my change was positive 5. If I'm going in the negative direction, I start out going negative 5 meters per second, and now I'm going negative 10 meters per second. What was my change in velocity? I'll give you a number. So my initial velocity, shorthand for initial velocity, was negative 5 meters per second. My final velocity, again, shorthand for final velocity, was negative 10 meters per second. What is the change in velocity? Louder, please. What'd you get positive 5? Why not? So you did negative 5 minus negative 10? Negative 5 minus negative 10 is positive 5. When you're looking at change, which one do you subtract from which? So you do final minus initial or initial minus final? I'm not quite, from the words that you use, I wasn't quite sure which one you meant. So if you start out with $10 in your pocket and you end up the day with $2 in your pocket, the change in the amount of money in your pocket was positive $8? Is that question mark? Do you have a positive change in the amount of money in your pocket if you go from $10 to $2? Change. There are not a lot of always in physics, but this is one of them. Change is always final minus initial. It's where you are, where you end up, minus where you started. Change in velocity is the final velocity minus the initial velocity, which is negative 10 minus negative 5, which is negative 5. So if I started out with a velocity of negative 5 meters per second, and then I speed up to negative 10 meters per second, I have negative acceleration. It would be really nice if you could break yourself of any thought that negative acceleration automatically means slowing down. That is not the case. Negative acceleration means that my velocity changed negatively. If I start out in the negative direction, if I change this negatively, I'm going faster. If I start out in the positive direction and I have a change, negative change, I'm slowing down. So we could bundle that up in just that if speeding up, velocity and acceleration have the same sign. If slowing down, velocity, acceleration, opposite signs. I did put in a request once to have the boards raised so that I wouldn't have to be doing that. The response was, "Tell me who's going to pay for that. We'll do it." When we were doing chapter 2, I talked about the fact that the total force has to be in the same direction as acceleration. So another way you can figure out the sign of acceleration is think about what are the forces involved, and we've gone through that, and what is the direction of the total force. So acceleration and total force always have the same sign. Let's think about what that means. Let's connect the two. I'm traveling in the positive direction, and someone pushes me in the positive direction. Will I speed up or slow down? I speed up, acceleration and velocity at the same sign. I'm traveling in the negative direction, and someone pushes me in the negative direction. Speed up or slow down? Yeah. I speed up, the total force was in the negative direction, my acceleration is negative, or I sped up, velocity and acceleration at the same sign. It works either way. I'm traveling in the negative direction, and someone pushes me that way. Pardon? Yeah. Therefore, does it have to change your answer? I was moving in the negative direction, and I get pushed opposite the way I'm going, so I have to slow down. So my acceleration is positive. Yeah. I slowed down, so they're opposite. So my velocity was negative, so my acceleration is positive. Or I was traveling in the negative direction, someone pushed me in the positive direction, so acceleration and the force are the same, which is that way, positive. All right. Good job. Positive, negative, zero. Position. Ray went somewhere else for the moment. Displacement. With gusto. Come on, like you mean it. Wow, that's like you mean it. I want to hear the voices in the back. That's the enthusiasm right there. Even if it's fake. Take the enthusiasm. All right. My displacement? My velocity? Oh, there we go. All right. My acceleration? All right. So now I'm starting here. Velocity is zero, and I start to move in that direction. Start to move in the negative direction. As I start to move, what's my acceleration? You seem unsure. Both of you seem to trail off there. Halfway through the word. You feeling confident? And you? Great. All right. The acceleration is negative. If I am here and I suddenly move in that direction, which way do I have to be forced? Yeah. The only way I can start moving in that direction is if there's some force applied. So I have negative force, negative acceleration. From a number point of view, I go from 0 to say -5. That's a change of -5. All right, so I'm moving in the negative direction and I slow down. My acceleration, correct? Right? Okay. Or slowing down so velocity, acceleration are opposite signs. Velocity was negative, acceleration was positive. All right. I'm moving in the negative direction. I slow down. I stop. I turn around, and I move back. So as I'm slowing down, my acceleration is positive. My velocity is 0 here, and then I start moving in the positive direction. So I go from no velocity to some positive velocity. So when I do this, what was my acceleration? Okay. When I stopped, because in order to turn around, in a one-dimensional problem, if I turn around, I have to stop at the extreme. When I stopped, what's my acceleration? Sounded like you said or.
Whenever you, at the instant you stop, your acceleration is still positive until you stop. I guess there would have to be a moment where your acceleration is zero, regardless.
At what moment would my acceleration be 0?
Whenever your velocity is
All right. That is a common mistake, so thank you for playing into that. Acceleration deals with change in velocity. If your velocity is 0 and acceleration is 0, if acceleration is 0, that means your velocity is not changing. You're in equilibrium. If acceleration is 0, velocity doesn't change. So if your velocity is 0 and not changing, what happens to you? Velocity is 0 and not changing. What are you doing?
being still.
Yeah. I wasn't standing still. I stopped just for a moment. You were right. My acceleration was positive at that moment of turnaround. There was not a moment when the acceleration was 0 in that small little second. That's a point at which it's easier to look at it from a force point of view. My force was in that direction. The force stopped me and then pushed me back, so the force was still in that direction the entire time. See, packing up going on here. Oh, we got another 7 minutes. Plenty of time. Questions up to here? All right, I'm going to show you a test level problem where you're doing this. This will be the last question on the first test, not this exact one, a problem like it. These letters represent moments in time. At time A, that is when the problem starts. Time B is when it turns around because it's initially sliding this way, it gets up to a certain point, stops, and slides back the other way. Time C, it's back at where it started. D, E, F, G, and then comes back. H, I, and then at J, it stops. Because this friction here loses some, it loses energy. And then the question is, when is the position positive, negative, 0? When is the displacement positive, negative, 0? When is velocity positive, negative, 0? acceleration, positive, negative, 0. I think that's the problem that I had on the desk last, not on the pre-test, this is on the test last semester. This is my starting point. I would have to tell you where the origin is, so we'll just make the origin here. Although I think I need a different spot on the desk. But it starts out with negative velocity, because I said to the right is positive. At B it's 0, the velocity becomes positive. Up until I get to G, then my velocity becomes negative. Until I get to J, then my velocity is 0. So my velocity is 0 here, B, J, and G. My displacement is positive anywhere to the right of my starting point. It's negative to the left of it. My position is negative anywhere to the left of my origin and positive anywhere to the right of it. Acceleration requires a much longer look at it. So if you want to get ahead, there's, if I remember, I'll post it also. So the one that's due in a week is the one dealing with forces. The one that's going to be due a week from Thursday will be revolving around this type thing. So hopefully I'll post that so that you can see it ahead of time. And I think on that note, I apologize for the 3 minutes. Don't worry, I'll get back to this another time. Have a good night.